let's be real, we are swimming in data. It's everywhere. Sports stats, company reports, you name it. So how on earth do you make sense of it all? Well, the secret is often finding just one number that can speak for the entire group. And today, we're going to talk about the most famous one of all, the arithmetic mean. Okay, imagine you're a teacher. You've got 3 different classes, and you need to know which one's doing the best. Are you really going to compare every single student's score against every other student? No way. That would be total chaos. The real question is, how can just one number give you a fair, quick snapshot of the whole group? And bam, this is exactly how it works. Forget looking at dozens of individual scores. Just look at one number for each class. Section A's average is 70. Tells you right away they're flying high. Section B is holding steady at 50, but Section C's average of 30? Whoa. That single number is a big signal that they might need a little extra help. See? One number, a ton of insight. So, this idea we've just seen in action, it actually has a formal name in statistics. It's called a measure of central tendency. And honestly, it's just a fancy way of saying it's a single value that tries to pinpoint the center, or the most typical value in a whole set of data. It's basically our anchor in a sea of numbers. All right, so how do we actually find this magical central number? Well, the most common tool, the one we all learned back in school, is the one we're going to look at now. So let's get reacquainted with our old friend, the arithmetic mean. The definition is actually super simple. The arithmetic mean, which you'll often see with this X bar symbol here, is exactly what you probably think of as the average. You just add up all your numbers and then divide by how many numbers you have. That's it. It's the average we use for pretty much everything. And calculating it using what's called the direct method is as easy as 1, 2, 3. Seriously. Step 1, add up every single value. Step 2, count how many values there are. And step 3, divide the total sum by the total count. Done. So let's try this with a real example. Here we've got the marks for 8 different students. Okay, step 1. We add up all the marks in this column, and that gives us a grand total of 360. Step 2, we count the students. Yep, there are 8 of them. And finally, step 3, we divide that sum, 360, by the count, 8. And there you have it. The mean score for this group is 45. That was pretty easy, right? The direct method is awesome for small, manageable sets of data. But what happens when our data isn't so neat and tidy? This is where our simple little tool starts to, struggle a bit. Just think about it. Imagine trying to add up the test scores of not 8 students, but 8,000, or trying to find the average income from a census with millions of people. Punching all those numbers into a calculator would not only take forever, but you'd almost certainly make a mistake. There's just gotta be a better way, right? And of course there is. Statisticians are clever, and they've figured out much smarter, way more efficient methods to handle these huge data sets. So let's take a look at the first of these slick techniques, the shortcut method. Okay, this is where things get really cool. The first method, the direct method, is just brute force. Add everything up. But the shortcut method, it's much more elegant. Instead of adding a bunch of huge numbers, it asks a smarter question. It says, hey, what if we just make a reasonable guess at the answer? Let's call it an assumed mean. And then we just calculate the average difference from our guess. This way, we're working with much smaller, simpler numbers. It's a game changer. Now, the absolute key to this method is a concept called deviation. And all deviation means is, how far is each individual number from our guess? You just calculate it by taking the actual value, x, and subtracting your assumed mean, a. Some of these deviations will be positive if the number is bigger than your guess, and some will be negative if it's smaller. Let's go back to our same 8 students to prove this works. We'll just pick a number that looks kind of central as our guess, our assumed mean. How about 40? Now, check out this table. For each score, we calculate how far it is from 40. The score of 30 is -10 away. The score of 60 is +20 away. We do that for everybody, and then we add up only these small deviation numbers. That gives us 40. Now for the magic. We take our original guess, 40, and we add the average of those deviations. So that's 40 plus our sum of 40 divided by 8 students, which gives us 40 plus 5, and what do you know? It's 45. The exact same answer we got before, but with way easier math. And believe it or not, it gets even smarter. For data that's really, really complex or all over the place, there's another level called the step-deviation method. It simplifies things even more by finding a common factor in all the deviations. But the main idea is the same. Always look for clever ways to make the math easier. So the arithmetic mean seems pretty solid, right? It's simple, it's logical, and we've got these efficient ways to calculate it. But it has one major critical weakness, a flaw that can make it not just unhelpful, but actually totally misleading. The whole problem really boils down to this one question. What happens when you have an outlier? One extreme value that's just way, way out of line with everything else in your data set. Let's check out the salaries at a small company. You've got 4 employees making pretty similar money, right around the $50,000 mark. And then you have the CEO making $500,000. That right there, that is our extreme value. That's our outlier. Okay, so first, if we calculate the average salary of just those 4 employees, we get $53,750. That feels about right, doesn't it? It's a number that really represents what a typical person in that group earns. But now, let's throw the CEO into the calculation and watch what happens. The mean salary just skyrockets to $143,000. Now, you gotta ask yourself, does that number fairly represent the typical person at this company? Not even close. That one single outlier has dragged the entire average way, way up, giving us a picture that is completely distorted. And really, that brings us to the most important thing to remember. The arithmetic mean's biggest strengths are that it's simple and it uses every single piece of data you have. But its biggest weakness is the exact same thing. Because it includes every value, it can be totally yanked in one direction by an outlier, giving you an answer that isn't really central at all. So as we wrap this up, just remember this. The mean is an incredibly powerful tool, this one number that tries to rule them all. But it's a ruler that can be very easily swayed by the extremes. The real wisdom isn't just knowing how to calculate the mean, it's knowing when you can actually trust it.